1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is it the total students is 11? 1, 2, 3, 4, 5, 6, 7, 8, and 10. Yes, I don't know whether the attendance is updated or not. Someone redraw or not. Okay lah, since most of you are here, I'm gonna start. This is the briefing. You can also get it from the Google Classroom. All the lab materials is in the Google Classroom. And I already mentioned 2 person in a group, so you can do it. It's a group work. The lab manual is here. This is the lab briefing. These are all the images for the computer output. You can just download and use it for the computer result. So you have the DC is shunt, series, compound. For the AC, you have delta and star. This is the cutout of the machine, as you can see. You have the terminal box, okay, on the top here. So that you can supply the DC voltage. Okay. And then we have the field winding, which is on the stator side. Okay, this is fixed. So generate the magnetic field, you cut through the rotor, okay, to make the shaft turn. Okay, this is the shaft or the arm of the machine. So you have the armature winding here, which will carry the induced voltage or generate the force or the torque to make the machine turn. The front here, you can see this is your commutator. Okay, all the winding is soldered to here, the front here, the commutator. And the brush is the rectifier, the mechanical rectifier. You can see here we have a brush. Inside here also one more brush. The rest are mechanical constructions. Okay, we have the ventilation fan here. If you click on this, there's a link here. Okay, you will go to a video I have made, the introduction here. Okay, if you're in the lab, you can see this cutout in the lab. So this is the shaft. If the machine turns in the front here, you can see the brush. Inside here, there's another brush to rectify the AC to DC. Okay, if it's a generator, you have the induced voltage. If it's a motor, then you need to supply voltage. You have the terminal on the top. So you can see the ventilation fan, the bearing there, all the windings inside. AC motor looks the same. Okay, the construction is similar, but it's more simple. You don't have the commutator and you don't need the brush. Okay, middle here you can see is a squirrel cage. On the top or the side here, you can see this is a magnetic field windings here, or the stator winding. Okay, the stator winding, you can either connect in star or delta. So that is the introduction. You can see that the AC motor has a similar construction, okay, but has fewer components or compartments here compared to the DC. Okay, no need to have a brush, no need to have a commutator. So the experiment is main two is a DC motor and AC motor experiment. You just need to come up with one report. Okay, the report should contain these two experiments inside. The result, discussion, all that. So the DC motor has 3 experiments: shunt, series, and compound. Okay, I've already drawn how to connect the shunt, series, and compound windings. So for the shunt, the E winding here or the field winding. So it's either, you can name it as a field winding because it generates a magnetic field, or it's called exciter winding. So it excites the motor to turn. So this is another name for the winding. For series winding, they use this D winding here, okay, to connect it to your armature winding. Okay, and a compound, they use both D and E winding connect to your armature winding. So the armature winding, you can see they use the symbol for the motor or generator. Okay, because it's also a winding. Some box they will use this as their equivalent circuit symbol. Okay. For here, they don't draw the winding in here, not enough space also to draw. Okay, and it's understood that the DC motor, the arm, okay, or the armature winding is the part that is turning. Okay, for induction motor, you can see that these are the 3 windings which will generate the magnetic field and make the rotor turn. This is your rotor. Here, there is no connection because we don't need to connect anything, plus, minus, no need. Okay, it will turn by itself. Okay. So the only thing that we need to supply is the magnetic field to make the rotor turn. So the magnetic field, we either can connect in star or we connect in delta. Okay, if we connect all these 3 windings in circle, is a delta. Okay, and then if we connect them in star, of course, the middle here is short together. Okay, as you can see, if I short like that, it's a star. Then the end of this winding will connect to the source, line 1, line 2, and line 3. Same with the delta, line 1, line 2, line 3. The induction motor, okay, we'll look at the equation next later. The speed, since they are not connected directly, this rotor not directly connected to anything, so it is slower to the synchronous speed. Okay, the synchronous speed equation is given by Ns equal to 120 F over P. Frequency we know is 50 Hertz. Malaysia uses 50 Hertz. Okay, is fixed. If in the exam you're not given either 50, 60, you can assume it yourself. You can assume 50 Hertz or 60 Hertz. Of course, if you are in Malaysia, you use 50 Hertz. Okay, then we can also determine how many poles this machine has the magnetic field pole. Okay, synchronous speed actually is you have some fixed value. For example, if the if we use 120 times 50, since the poles is all in pair, it can be 2 pole, 4 pole, 6, 8, and so on. Okay. So how many poles we have? Actually, we can refer to the nominal speed of the machine or the rating on the machine. Okay. So for connecting hardware or doing the experiments, okay, actually, of course, you need a power supply. Okay. We're doing motor experiment, so not a generator. So we're doing, if we do generator, we need an external prime mover. So that's why we don't have, we don't do generator experiments. We need something to turn the shaft, okay, to make it as a generator. So for students experiment, we mainly do motors. Okay, hardware connection as usual. Number one, the input. Okay, we have the input, which is a power supply. Okay, protection system. Okay, before you go to the machine, of course we need some protection system. Usually we have fuse, okay, switch box, and so on. Okay, switch boxes. Switch box, we use it for the AC. We can switch between the star delta connection just by using a switch box. Okay, and after protection system, since we are doing experiment, so our objective is to find the efficiency for the motor. So what is the equation? Output over input power. Okay, to find or the output for the machine, actually we need to fix the output. Since we're finding efficiency, let's say you're selling the motor to the customer for 1 horsepower. So actually the efficiency that you measure must be 1 horsepower, okay, according to the output rating. Okay, so we're actually in this experiment, we want to fix it according to the rating. Okay, and we say rating is always output. A customer buy a motor 1 horsepower means, of course, this is the output that they want, not the input. They are not interested in the input. Okay, and motor same like when you manufacture anything lah, you will have different efficiency also. Okay, so even if I have 100 motors that is 1 horsepower, of course they have different efficiency. Okay, because depend on the manufacturer, it depend on the condition of the factory also. So input, how do we get input? What's the formula for input? If we have a DC, we have volt times current. Okay. But if we have AC, how about AC input? What's the formula? Circuit 3 VLIL cos theta. Okay. The difference between AC and DC is just this constant, circuit 3 cos theta. Then you get the AC. So we actually need to measure all of this. Okay, circuit 3 is a constant, no need to measure. This one need to measure also. So voltage, current, and power factor. This is our measuring device. Okay, you need to measure the voltage, current, power factor. So we need to connect the measuring device to the motor. Okay, for the power also, actually you need to measure, right? We need to find, or we need to fix the power at this output. So we need to know the torque and the speed. Okay, divide by 9.55. So here we need to have a torque reading, we need to have the speed reading, which we can get from the tachometer. And then we can control the torque going to the machine here. So there's a control system here, okay. To control the torque, of course, we need to have a load, okay. So this control system actually is connected to the load, okay, so that it control the torque up or down, okay, vary the torque, and then we can also read the speed here. So next, we're gonna look at the input, okay, one by one here, power supply, the protection system, the measuring device used. I'm gonna look at the motor, the machine test system. This is called the machine test system, okay, to control the torque. So the DC motor looks like this. Okay, you have the end here is the motor. You can see that we have the connectors slots here, A1, A2. Okay, then we have the D1, D2, and D3. And then we have E1 and E2 is here. The symbols, okay, is the same as you can see, is drawn at the motor here. So if we connect them accordingly, okay, we can do the experiments for shunt, series, and also compound. Okay, the shunt and excitation field winding is the excitation field winding is just now I explained. E is either called E or is called F. Okay, this E and F. And then the machine, you can see you have the shaft, and then of course the end of the shaft is connected to a load. Okay, this is connected to the machine test system so that we can control the torque, okay, which the machine can drive. And the power supply to the DC motor, you can see we have the power supply to the DC motor. If let's say you're in a factory or you're working already company, or you go to industrial training, so how to use the device? Okay, you can see here, you also have the terminals plus minus. Okay, but it is fixed here at 200 volt and 6 amp output. So actually this side we cannot use. Okay, the motor, the DC motor needs 220 volt. So here we can use, since it's more than 220 volt, okay, we can use the knob here to control the voltage. The knob here is to control the current. So the motor only use about 1 something current. So we can go tune it halfway is enough. If too much current, maybe you spoil the motor also. And voltage also, we increase it slowly, okay, until it's at the rated value, so it doesn't suddenly speed up. And then this side also we are not using. You can see, you can read it yourself, it's 10 volt only, so this also not using. So this is the terminal that we will use to connect to the DC motor. Okay, that is power supply. For the AC motor, okay, it looks similar to the DC motor, okay, except that the connectors, you can see only for the 3 windings. Okay, then you have a symbol here which represent the squirrel cage or the rotor, which does not need any connection. Okay, and it has a 3 face or the symbol here, which represents an AC machine. And then you can see that the arrangement of the connectors. U1 is here. Okay, this terminal. U2 is over this side. Okay, V1 is here. V2 is over the other side, opposite it. Then W1 is here. Then W2 is here. So why they arrange like this? Okay, the reason is that it's easier for us to connect it manually. If let's say we want to connect as a star, okay, we're going to short here together. This one will go to line 1, go to the line 2, and here we go to line 3. Okay, this 3 here go to the lines terminal. So if I short in the middle, it will become a star. How about delta? If we want to connect for delta, the only thing that we need to modify when we want to do delta is to connect in delta, we need to connect the windings in a circle. Okay. So let's say I have a U1 here, U2 is here, and it's connected to the next winding. Let's say it's V1. Okay, here we have V2. Okay, here sure will be the W winding here. We left with the W winding. So let's see. Okay, here is W1. Here will be W2 lah. This is a delta circuit. Okay, you can see it's a circle. Then the rest will go to line 1, line 2, line 3, same lah. The top here, no change. Okay, line 1, line 2, line 3. The bottom, you can see it needs to connect U2, connect to V1, V2 connect to here. W2 here, connect to U1, go back to here. So it will form the delta. So if you look at this connection, you just need to change the wire go to the bottom. Okay, you can see that W2 will connect to U1, U2 is connected to V1, V2 is connected to W1. So this arrangement will make it easier. This one will become a delta circuit. Okay, so it is more convenient to arrange the connectors like this. The others are the same. You have shaft, you have the load, which is controlled by the machine test system. The drawing of the connections are here. Okay, I've already explained. Okay. This side actually represents the motor connection. Okay, here also we have the delta. So if we want to control the machine top, okay, this is the machine test system. On the top here is the input power. If we have a B plus, then this is a V minus equal the DC. If for AC, we have line 1, line 2, and line 3. DC, the third one we not is, you can just leave it open. Okay, you are not using. It is for DC. For AC, we connect all 1, 2, 3 go to the top here. This is the input power or input terminal. The bottom is going out to the motor side, okay, to the motor's winding. For the experiment, you can see this actually is to press it on and off the top control. Okay, the control mode we are only using here, the top control. The rest is for other modes. If we have other machines, if we have generators or we have these are actually some equation for the motor equation. We have flywheel. So for our experiment, we only use the third mode here. And this knob is to control the top, either increase or decrease. Okay. Clockwise is increase, Okay, if turn back is decrease. And then you can see the reading on the top here. This is to show you the speed, okay, in RPM. Okay, speed usually is 4 figures. Okay, it's just the same like your car. Okay, your car is like 1, 2, 3. Then middle here is times 1000. Okay, this is in RPM. It's like the meter of your car. And then for the torque control, you can put in the torque, okay, up to 2 decimal point. Okay, how much torque that you put in Newton meter. Okay, this one we can control it. The speed we cannot control the speed. We can only read the speed. Okay, the thing that we control is the torque. And then this, okay, will go to the load. And this is to control the load here. Okay, the connectors. This should be going to the load. And then this one we have going to the computer. Okay, we also can control the torque from the computer side. Okay, then plot out the graphs. You can see the power supply go to protection system. Okay, there is a few protection system that is used. Okay, for the DC, you can see this is the fuse box. Same like if you want to connect to your house. Okay, this is the fuse. It will switch off if it's over the limit. The limit actually is written here. I think it's around 1.6 amp. Okay, the input, how to connect. Okay, it's just like a switch only. Okay, the power supply input go to here, then output will this plus and minus, then only will connect to your motor side. Okay, so it's between the source and the machine. Okay, so there's some protection system in between here. We can also use this starter to control the current. Okay, when we start the machine, the current is very high. Okay, it's equal to Vt over the R. This R actually is your armature resistance, because you can see here, this is the resistance, and here it only goes to your A winding or your armature winding. Okay, so your E winding actually it bypass. Okay, so your IE usually is very small. Okay, so it doesn't need protection. And then when we connect the load, we are connecting it to A. Okay, the load will go to your armature or go to the shaft. So your E here actually doesn't need any protection, okay, because we just need to generate the magnetic field to run the motor. So actually this is something bypassed already. You don't want to connect here also, never mind. You can like straight away go to the terminal positive here. Okay, but since the positive already go to this point, so here they have an extra point for you to go to your E winding. Here we go to the A winding. So we can control the amount of current flow. You can see here the current they can let through how much. So this is actually the percentage. This is just written in percentage, because resistor also this is a variable resistor. The starter is actually a variable resistor. Okay, if we turn to here, we're using all the resistance. If we turn to here, then this one becomes 0 ohm. Okay, means we after the motor start already, you will have the induced voltage. So once the machine already start, okay, this one already go up. then we can reduce this external resistance, okay, so that there is no extra loss. If not, when you calculate the efficiency, then you have extra loss, okay, before you go into the winding. This is for the AC. How about the DC? DC, the input power to DC, like I mentioned, you have line 1, line 2, and line 3. And you can see we use the 3 different colors here: red, blue, black. If you don't use, if I all use red, actually you don't know which line is which. Okay, same like my house here. The renovation all use one color. I also don't know which color is which. Okay, so it's a good practice to do different colors. Okay, for red, or you have different terminal, plus, minus. So this one actually comes from where? This is actually from at the experiment table there lah. So this is actually a transformer. Okay, if we open this out, this is actually a transformer. Okay, inside here. So we have the fuses also to protect this transformer in case that we connect wrongly. Let's say we accidentally short line 1 and line 2 together. Okay, very dangerous. So it has a fuse here. And then you can see that you have a knob here also. This one you will control the voltage. Okay, the voltage you can see only go up to 500 maximum here. Okay. So, but if we look at the rating here, okay, for the motor, okay, when we want to read the rating, we can get it from the machine's plate. This is called machine's nameplate. Okay. So this is for star, then this is for delta. How we know? If they never mention, you can use logical thinking. Okay, you can see if it's higher voltage, it's usually for star, and then if it's lower current, it's also for star. Then this is higher current is for delta. So you have star delta rating here. Okay, the reading. So they use a slash like this. So the star actually needs a higher voltage. Okay, this is the rating for the star, 690 volt. So the delta is 400 volt. Okay, the power rating is here. The speed, okay, nominal speed rating is here. So for AC, you can see that the voltage for this transformer cannot go up to 690. Okay, it stops at 500 here. So our experiment, we can only use the V line, which is equal to 400 for both star and delta. Okay, so our equation is SERT3 VL IL cos theta. So this VL actually is fixed at 400. So you don't have to convert anything already. Okay, because it's not possible for us to use 690. Okay. Of course, this is for the line voltage. We are not using the phase voltage. Okay. We just measure the line voltage here, and then we measure the line current, which later this one you go into your winding. Okay, so this one will be measured line to line. Okay, line voltage, line current, and the power factor also. And for the motor protection, for the AC, it's the same like the DC, except that we need to connect all of these three here. Line 1, line 2, line 3 go in here, go through the fuse or the trip here. And then again, this one go out to the motor side. Okay, line 1, line 2, and line 3. If we are using a switch box, okay, this is called star delta switch. Okay, the line, then we will connect it to here, to the switch box. And then this one straight away go to U1, V1, W1, and so on, U2, V2, W2. So this connectors straight away we connect to the motor here. Okay, so that we don't have to switch between star delta. We don't have to manually take out the wires when we want to do star delta experiment. So this one straight away you go to the switch box. Okay, straight away. You don't have to use your brain. Don't need to like change here, we need to short here. No. So this one straight away all go to the switch box. Okay. If U1, then go to the U1 of the switch box. Okay, U2, then go to the U2 of the switch box. The switch box actually is, I forgot to download this star delta switch box. Okay. You can search it yourself also. Let me find the diagram back. Where is the diagram already? Yeah, this is the diagram. So the star delta switch box looks like this. Okay, this is a triple pole double throw switch. Okay, triple pole means we have 3 phase here, we have 3 poles. Double throw means we can switch between star and delta. You can see that the switch inside here, of course, we need to short the middle to get all the windings middle here, the middle of the winding here to get a star connection. Okay, you can see if this wire will go to the winding at the ends of the status winding. Okay, the stator winding is a field winding. Okay, and this is the squirrel cage, the motor. So it's not connected to anything. Okay, it's a free running. And then we can see that the winding, the ends of this winding will go to line 1, line 2, line 3. Okay, so if you switch it to delta, okay, you can see that you complete the circle connection. Okay, it will be in a circle. So this is make our life simpler. Okay, so that we don't have to manually change the wires. And it also acts as a protection. Okay? Because when we start the machine, you can see what's the advantage. Okay? It also limits the current. How it limits the current? By 1/3 is if we start it as a star. Okay? Because just now the rating, you can see that for delta is a higher current. So how to protect the AC machine? We can start it as a star motor first. Okay, after it starts and run, then we change it to delta connection. Okay, so that the starting current will not just jump too high. Okay, it will slowly go up to the delta. So besides conveniently switching, star delta is used as a protection system also. And then also connect to the machine test system lah. Next, we're gonna look at power supply, done. Projection system, done. Next is voltage, current, power factor. Of course, I'm using digital meter because it's easier to read from the video. Okay, just a revision on how to use meters in case you forgot. Okay, you cannot use also unless you have a meter at home. Do you guys have a multimeter at home? If not, you can buy one. It's useful to, let's say, and you can fix your lighting lah, whatever lah. Just a simple one. You can fix it. In the lab, we actually want to use the analog meter lah. Okay. For the Assgn experiment, I am using the analog meter, which I film it quite close lah, so that you can take a rough reading. You don't have to be very accurate, because that one is just to observe the starting current. Okay, so that we can see the needle jump to where, and then it will slowly go back after it reaches steady state. Okay, the starting current will jump to a higher reading, then it will go back to a stable one. If I use digital meter, it's a bit hard to observe it because there is no needle to see. There is no moving part. We can only see the reading go up, then suddenly the reading will go down. Okay. So it's easier, it's better to see using an analog meter lah. So how to read the analog meter? For our experiment, we only use it to measure current. Okay? So we have to, of course, connect them in series with the winding. Okay, this one is going in, then this one is going out. Okay, so we have to connect to the two terminals lah. Same if we have a component. If you only connect this, then you forgot to connect this. This is open circuit. You are not connecting it to anything. This go in here, then never go to anywhere. If you don't connect the second leg, got one leg, got two leg, must have two leg. So each measuring device, same thing. If you only connect in, you don't connect the out, is open circuit. Current go in, then doesn't go out. Okay, so nothing to do. So make sure you do the both connection. These are the scales. Okay, let's say I switch it to 3 amp. So the label I use it to read is 0 to 3 lah, the bottom one. Okay, 0 to 3. If I turn it to 1 amp scale, okay, 1 amp means I will read 0 to 10, but I will convert it from 0 to 1. Okay, means it is 0 to 1. So whatever I read, I'll divide by 10 lah. If it's here, means it's 0.2. If it's here, it's 0.4 and so on lah. You follow the scale here. The scale here means it's the maximum scale for the meter. Okay? If of course 10 turn to 10 amp easy lah. Just read on the top here. If it's turned to 0.3, then read the bottom, then divide by 10 lah. This is actually to read the voltage. Okay, if we connect this, and this is to read voltage. Okay, if we connect these two terminals. Digital meter, if you want to use also same, this is, you have to choose the scale also. This is for AC, this is for DC. Okay, this is for smaller voltage. Okay, either DC, AC can use. Okay, this is to measure capacitance, measure the connectivity. The diode here. This is to measure the diode. This is to measure the connection connection. Okay, if it's how much ohm also you can measure. Okay, if there's no connection, short circuit, you make a sound. If you turn to here, this is ampere, okay, milliamp, microamp, and then turn it off lah. Since this is a cheaper digital meter, so you have to connect the probes manually also yourself. Okay, the probe is not fixed. Some if more expensive one, the probe is fixed. This one you have to connect, okay, the probes plus and minus yourself. If you measure current, you have to connect plus minus like this. If it's milliamp, then you connect here. If it's voltage, ohm, you connect to here. Okay, so you have to change the probe yourself manually. This is the scale. This is just a bigger view of the scale, then how to convert the reading. I also have a video lah, but you can go and watch it yourself. Just want to save time. This one I already explained. Here, if you click this, I also got put in a menu. You can find the data sheet here for this menu here. Okay, the equipment description is all here. Okay, what are all of these? Just now I explained already. This is the RPM. This is the top, and then this 4 indication here is to indicate the machine's operation. Okay, there's a M label here, means it's a motor mode. If not mistaken, then this side it will be your generator mode. Okay. If we start the machine, usually it will light up maybe on here for the AC machine. Okay, because there is no load to it, so it is like a generator mode. If the light goes up here, this is clockwise direction. If the light is light on the bottom, it indicates counterclockwise direction. Okay, this is called the 4-quadrant display for the machine. So let's say next time you go out to work and then you don't know what that equipment, how to use that equipment. Usually you can go and Google the number of the machine description. Number is here, 731989 USB. Actually, you can type this in, then you can Google it out. Okay. Then you can get the data sheet. There are even some example experiment or setup here. Okay, that is suggested. So this is actually the data sheet for it. Okay, and this is a German equipment lah. So and then it's able to be Googled out also, okay, on the internet. This is an instruction set for this device. Okay, which I mentioned you can Google it out. If next time you go out to work, no one teach you. Okay, this is what you need to do. Okay, Google. The Google is your teacher nowadays. YouTube and Google, you can learn anything from YouTube and Google. Protection equipment, measuring equipment. Okay, for the AC, we have one more measuring equipment, which is a power factor. You have the input, okay, and the output. Then this is go to neutral. So we need to connect these three to the machine so that we can do the power factor reading here. You can see that the scale is 0. It's not even. Okay, then go to 0.5, it's quite far. And then here 0.6, 7, 8, and 9. So it's according to the cos theta. Okay. Bottom here is the angle. If you read bottom, you need to convert. You need to use cos theta to convert it. It's very hard to do the reading from the meter, so I take the video on the computer screen. The computer screen also can output the power factor. Okay, this device actually can measure the power factor also, which will input it to the computer side. Okay, so actually we can read voltage, current, everything from the computer. Actually, if we don't use this measuring device, but is in the lab you need to connect it to learn. And then we have a capacitive load. Okay, it is to correct the power factor. Okay, it is a compensation device. Let's say for the AC we have delta circuit like this. Okay, if we want to have a better, or we want to reduce the current consumed, okay, we can connect the capacitor to it. Okay, this is the capacitor bank or the capacitor load, which will connect to the machine so that we can reduce. Only for delta because for the star the current is too small. We don't have to do anything for the star. Delta is, then we can reduce the current for delta. I think that is all finished already. I already done all of this briefing. Okay, next is we're gonna see how we're gonna write the report. Okay, the procedure to do the experiment. Okay, is first we need to determine the top value. Okay, that we need to enter to the machine. Like I mentioned, the objective is to find the efficiency. Okay, but to measure the efficiency of a motor, this output reading, we need to have it fixed at the rated value. Okay. How to know the output? How much is the power output? Okay, we can get it from the nameplate, okay, of the machine. Each motor comes with the nameplate which you also can Google nameplate. Salah pula. Okay, that motor nameplate. If we see the images here, there's so many, okay, which we can use it as an example also can. Okay. Like we can know what is the rating, voltage, current, so on. For example, this one, 50 Hertz. Okay, you can see the rated speed, RPM here. It can also operate at 60 Hertz, but it's at different nominal speed or the rating. You can see it change. Of course, it's faster if you use 60 Hertz. And then we have the difference voltage here. We can operate at different rating. Then you have the range. So we have the I think delta and the star connection here because it is induction motor. Okay, so you can see that the star has higher voltage. Delta is a lower voltage, but higher current here for delta. And then the star, we have lower current. Okay, this is how we know. You can see that there's a yellow box here, okay, which indicate the output or the horsepower. It's 18 or 180 watt. Okay, so this one is the output power. Okay, or 0.25 horsepower. So this one will tell us the output. Input, you can see there's a range of current. So it's up to you lah. Whether you want to operate at 220, 240. So output here always is fixed. Okay. But we're doing experiment. Okay. So how to make sure that we get this output? How? We need to control the torque. Okay. So to get that same output power, okay, so how are we going to control this motor? It's using the machine test system, right? So we only can control the torque here, either increase or decrease the torque. So that if controlling the torque here, we will get the power output, okay, which is torque times the speed over 9.55. And I mentioned this, we cannot control. This is uncontrollable, so we can only control this. So we want to see how much to input in order to get this power. Okay, so if we have the reading for the power, we have the reading for the speed, so that we can find how much torque we need to input. Okay. So using, this is for DC motor, okay. So you guys calculate what is the torque that we need to input to the machine so that we can get the output. Guys, use your calculator and calculate. Okay, and then the formula will become 9.55 times P over N. From the nameplate there, we have 9.55 times. This is 300 watt, and then the speed is 2000 RPM. Okay, you can see here. Okay, the rest is not used, so I'm gonna leave it first. Guys, calculate what is the torque, or the nominal torque, or the rated torque. Okay, so the answer is 1.43 Newton meter. Okay, this is what I got from the rating here. Okay, same for AC motor. We can also determine the torque using the same equation because the procedure is the same. Okay, the only difference is when we calculate the input power. Okay, this is in 270, we have 1350. Procedure is the same. Okay. You also determine the torque. Okay, but this torque, after we determine, actually is for delta. Okay, because we are actually operating at 400 volt. Okay, so that this 400 volt actually is for delta. So if the star also operate at 400 volt, so what will be the torque or the star? By right, it should operate at 692 volt. Then it will be the same torque as the delta. But since it's not operating at its rated value, so it's operating at lower. So we can actually use, just divide by 3, okay? It's 1/3 of the delta torque if we want to get the star torque. Okay, so this DC motor has 1.43 as a rated torque. Okay, so, but that one is just the nameplate, okay? Same like a resistor. The resistor has a color code also. And then it has a, behind here, what is this? It may be 5%, it may be 10%. What is behind the resistor here? Guys? Huh? This is the tolerance. Correct or not? I buy 1 kilo ohm, but it can be plus minus 5% of this reading. Same like the motor. The nameplate here says it will output 300 kilowatt, but it's not necessary that all the motor, after I put in 1.43 Newton meter, it will give me 300 watt. Correct or not? It's not necessary I will get 300 watt. Okay, so this is our experiment. Our aim is to get 300 watt. So, but of course, I don't start my value from 0 top. Then I slowly increase 0, 1, 2, 3 until I get 300. Okay. Of course, we can use the formula P equal to Tn over 9.55. When we do the experiment, we can slowly increase 0, 1, 2. This one will take forever. Correct or not? So we use the nameplate there. Okay, we calculate. This one will become our reference. Okay, this is the input. So if I input 1.43, and then I get the speed here, let's say is 210 lah, and I input 1.43. Using your calculator, or you can know that this will not give me 300, okay, but it might be higher because this speed is higher than the rating lah. Okay. By right, I want to get 2000, right? The speed. If I use 2000 times this, I will get back 300 watt. But the motor has some tolerance, has some difference also. So each motor is manufactured differently. So if it doesn't give me 300 watt, what do I do? If it gives me 305 watt, do I take this dot in as my efficiency? Can I do this calculation for the efficiency? No, right? If I take this value, it means I'm calculating for a higher watt rather than 300 watt. So in the lab, what we do is we tune the top, right? We calculate, okay, then we set it at the nominal rating, okay, that we calculated. If it doesn't give me 300 watt, I will adjust the top, okay, up, down, until maybe I will get 299.99 watt. Okay, this is satisfied, lah, almost same. Okay. Then I'll take this as my final nominal rating, okay, or the actual nominal value. It might be smaller, only like 1.42 maybe, okay, or 1.41 also can, or 1.40 also can, depend on your motor connection lah. So each time we change the motor, we will, okay, verify this again, okay, verify it again. We put it to 1.43, we run it, we adjust it. Of course, this one I already did lah in the lab. So your job is just to jot down the result. Okay, I'm just telling you the procedure here. Okay, but for this, you only get 1 point, which is V times I. I measure the voltage, I measure the current, and then I measure torque and speed. Okay, measure, then I get efficiency. Yay, done. Finish experiment. Correct? But doing this, you only get one result. So we don't know whether the motor, how the motor characteristic, whether it's linear, non-linear, go up, go down. So we have to have multiple readings in order to have a graph, to have a plot. If not, just now that result can also, but we only have one reading like that, a dot that doesn't go anywhere. So you cannot do any conclusion. You don't know whether this motor is linear, non-linear, or whatever. So in order for us to have to plot the graph, okay, so we vary the input torque 0. Then next point, this is in per unit. Okay, this is the gap that we want to vary it. 0, 0.0, 0, 0.1, 0, 0.2. This is the gap that we want to vary the torque against. Okay, so this is the actual torque that I will put inside the machine. I will tune it according to the nominal torque that we found that will output the 300 watt. Okay, so this is the gap that we will create. So it will give us increasing or decreasing, okay, values. Okay, of course, if we have less torque, current will go down, correct or not? Okay, if we have the IA will go down if it's less torque. If I increase the torque, of course the IA will go up. Okay, so this is something that we want to see. Go up how much also we don't know. Okay, so we need to vary according to the this torque value. So we just times the actual torque that we found according to the per unit values here. Okay, 1 to 1, of course, here we will get the actual values. If it's 1.42, then it's actually 1.42 lah. Then here is lower, here is higher. Okay, so this one will get 0.14 and so on lah. Okay, so this one is the per unit values. Then after that, you measure all the things. Okay, measure the current so that you can use this to find the output power. Use the formula. P2 is the output. And then we can use the formula V times I. Okay, V times I, then you can find input power. Okay. Next, but we want to plot everything under one graph. So to plot everything under one graph, we need to change it all to per unit. If not, this power is 300 watt, this current only 1 amp, 0.1, 0.2. So you cannot observe everything in one graph. So to observe everything in one graph, okay, so all of the reading is changed to per unit. Okay. How to get the base value for the per unit? Guys, how to get this IAN, IEN, or P2N here? Some of you might take this value as your IAN. Okay. You might think that, oh, this is IA ma, then I take it as IAN ma, my nominal value. This one is my IE. Is the smaller current is your IE lah. Higher current is your IA at the amateur. So you might think that I can take this as my IE lah. But let's say it's not operating at the nominal that you calculated. It's not 1.43, you found is 1.42. So everything will change. Okay. So what you do is, this is the lab manual. So what you do for your lab report is, you take whatever reading that you get at this 1 per unit here, okay, as your base value. Okay. If I use 1.42 here to do the experiment, so this whatever I get here will be my nominal value lah. So that when you divide n with n, you get 1 here. Also here you get 1. Here you get 1. Okay. If you don't use these values as a base value, most probably here you will get maybe 0.9 or maybe you get 1.5 because you're taking from the nameplate, correct or not? Rather than taking it from the experiment. So make sure you take this at 1 per unit as your nominal value or the base value when you want to plot the result. This is just the computer lah, software that is in the lab. Okay, we can use it to determine the load and run up characteristic of the machine. This is plot against speed, so it's different from this one, the manual control. It's different from this. So you do two discussion. You do one more observation. This is against the torque. This is plotted against the speed. Okay, so this is actually just to observe the response of the machine. Then you can also choose a different type of machine to run: shunt, series, compound, and then the squirrel cage motor. Okay. These are the settings. Okay, just so that you guys see only. There are other settings here. Torque control, we already, this is used manually lah. We manually do it. This is using computer. This one not doing. Okay. So I will go to the lab manual, explain on the lab manual. The contents are all here. Okay. You can also click on the table here if you want to go to one of the content. These are just the links within the document itself lah. Okay. If you scroll your mouse over here, if it says YouTube video, then there's a YouTube video for you to see. If not, it is just a link inside the document. For example, because I scare you guys to ask, hey, the link broke. This one don't have YouTube video. Actually, that is not. There is no YouTube video for that link. It's just for me to, for example, this one nameplate. I click here. I will go to the appendix. It's just for me to see easily. For example, okay, you want to get the rating. I already attached to the appendix A and B here for the DC motor rating and then the AC motor rating. This is the rated voltage, 220 volt, okay, and the power, rated speed. This is the amateur current because it is higher. Okay, although they never label, use your brain and think lah. Okay, IA is higher because it's at the amateur side. Okay, it needs to drive the load. And then, of course, Malaysia is 50 hertz. Okay, this is European country. This is from German. It's also 50 hertz. And then this is IE because it's lower current, 0.25. So this is the current for IE. Okay. And then for here, this is the rating for the induction motor. Let's go in. It's very blur. That's why I retype all the rating here. Okay, if not, it's hard to see from the picture also. there is a typing here. If you guys can see, this is */delta lah. But if they never mention which one is which, use your brain. Okay, higher voltage is star, lower voltage is delta. This is the power output, since it's only one machine or 1 hour power lah. The speed, again, this is lower current star, this is higher current is for delta. This is the power factor for this machine. Okay, not necessary, but this is just for reference. And then this is 50 hertz. The experiment, you have to read it from the video. It's not necessary at 0.7 also, depends on the machine. The first experiment is shunt motor. The connection is, this diagram is the actual figure of the connection. We are not using this. Okay, this is just for illustration. The diagram, circuit diagram we use for actual connection is this. Okay, we follow this. How to read the diagram is first, okay, from the source, you have the plus, go in here, this is the fuse. Okay, the first input to the fuse. Then the output at the fuse will go to here. This is the starter, the starter. Okay, the real start. Okay, just now we see the figure there, you have the A will go to the A1. Okay, and E here is a positive also, you go to the E1. Okay, then the negative will go to A2 and E2. So we can draw the equivalent circuit by looking at this diagram also. Okay, so draw equivalent circuit. Okay, let's say plus. Always start with the terminal. Okay, plus minus, this one, the line. Plus minus. This is a terminal voltage. Then go in to the machine. Okay, here we have a starter. Lama. My pen not listening to me. So here you can see that you have A winding. The symbol we're going to use is a motor for the A winding. Same like the symbol at the machine there. Okay, so we have A1. And then here the negative side is a A2. Okay, and E1 also is connected to the positive. Okay, you can see there. So here we have the E1. And then we have the winding. Got E1, of course, got E2 lah. E2 here, you can see this is a short together. You connect them together, so you have E2. So looking at the diagram, you can see this is a shunt motor. They are parallel to the voltage source. Okay, they are parallel. If you want to measure the current, you can put a meter here. And put a meter here, so we need to put a meter here and a meter here to measure the current flowing to IA and flowing to IE. The direction of rotation for DC machine we are all doing is clockwise. You can click on the link there and then you lead to this video here. It is clockwise because looking from the shaft, not from behind, from the front here. And you can see that it's rotating clockwise. But this is too fast. But still can see. So next, you can see there's a link here also. You can click on this. Then you can fill up the table here. Okay, this is starting the machine. It is connected to the starter. Okay, and a few starter here. This is a shunt motor. I leave it at this 51 volt. So what happens if you run the machine at 51 volt? Guys, and then turn to 220. So what do you observe? Guys, 50 volt. Okay, running at 50 volt and one more running at 220 volt. What is the difference? Huh, guys? If we run the voltage 50 volt, can or not? If we do the experiment, I simply just put in any voltage. Can or not? Why cannot? It also can turn, ma. See, 50 volt can run also. 50 volt, like that. Cannot simply do like one. 220 volt Malaysia? No That one is just that rating ma. I can also use it at 50 volt ma. I like lah. Cannot meh? What if I operate at simply any voltage? What if I simply operate at any voltage I like, rather than like the rating here, 220 volt? What will happen? Then the efficiency you calculated is also out lah, correct or not? Although this is V times I, actually this V is fixed. This one change. Okay, this output actually we fix it also. Okay, but if we run a lab, okay, we vary it according to the per unit value later on for this stock Okay. So when we calculate efficiency, this output is fixed. Okay, this voltage actually is also fixed at 220 volt. Okay. So the only thing that governs the efficiency here is the current. Correct or not? Different device have different current rating also, different requirement for the current. Okay. It's same like you eat one plate of rice, but your output is different from A and B or C person, right? Okay, you burn different calories. Same thing here. Okay, you need to give 220 volt. Okay, if I put 200 volt, what will happen? Then this calculation will be off. Okay, you're supposed to eat one plate of rice, but you're on diet. You say you're on diet. You eat half plate of rice. Cannot. You must eat all the rice. Okay, if not, it's a waste. Okay. If you operate at 200 volt, the motor can even turn at 550 volt ma. But why we don't turn it put it at 50 volt? Or we don't put at 10 volt like that. Okay. Actually 50 volt later, actually you cannot turn the top. Okay. Then it's not enough power to turn the top also. Correct or not? It's not enough power there also. Okay. But what do we observe in the video here besides why we need to set it at 220? Okay, Did you guys attend class yesterday? Maybe you are sleeping. Is the video too boring? Okay, you can see that lower voltage has a lower speed. Correct or not? Okay. So higher voltage, we get higher speed. So we can use the voltage to control the speed of the motor. So that is one type of control. Another is we can use this. Okay, we will start here. Okay. For the experiment, we are first turn to 100. Okay, is starting at 100 ohm here. 100% of the ohm. Then I turn it to 0 ohm. Okay, then you can see that the speed. What happened to the speed? Okay, the speed. What happened to the speed, guys? From initially this to this. Guys, don't know what happened. Okay, the speed will increase. Okay, but you can see the motor speed actually is not a stable thing. It keep on increasing. Okay, so actually I cut the video short already. If not, you need to wait very long time to get the steady state speed. So internally they have an induced voltage, induced torque. So you need to counter this load and so on. You need to reach a steady state speed. So it will take some time for the motor to reach the steady state speed. So actually in between here, I cut out the video so it's become shorter. If not, you have to stand there wait for a very long time. Then you can jot down the final speed as you're reading here, or you can jot down your observation. Okay, you can write it in your report. So those things that I asked is the observation the question that I asked. For example, you can control the speed using the voltage at the terminal, or you can control it using the starter, which you connect to the armature winding. Okay, that one is just for the using starter, the observation. Next here is connected to the machine test system. Okay, this is the machine test system. So we'll measure IA, IE. Okay. So this one just now we already did lah. We already measured, we already calculate the, and this is calculation. Okay, so this is 9.55. This is PN over the nominal speed we got is 1.43. Okay, using the same procedure. So we find what is the actual nominal speed. Okay, this one. Again, this one is not YouTube link. This one is just the equation that you can get from the appendix. This equation. Okay. This one also not a YouTube link. This is just the appendix there. So that you can fill up the table. Okay, to know what is a nominal speed that I use, you can click on this video. So this table here, you need to get it from the video. Click on it. You can see this is the shunt characteristic experiment. For the shunt characteristic experiment, I start from 0 because first thing is I verify the nominal torque first. Then based on that nominal torque, I created this table. Okay, I already created that table. Then I run the experiment. So the first torque I put in is 0. You can put down here 0. Then you can read what is the speed and then the current from the video. The rest here is your own calculation. This calculation I already did it. I already found the actual torque. I already multiply in. This one you actually get from the video. Okay. You don't need to calculate it out. Calculate here means the 0 times Tn. This is 0.1 times the Tn. 0.2 times the actual torque, nominal torque, and so on. Okay, then this calculation is you calculate using an equation or using this. Okay, if it's to find the per unit, this is to find input. You know how to find input Vi. This one is output, torque times speed divided by 9.55. This is per unit. Okay, efficiency, you know how to calculate lah. Output over input. This also, all the measurement get from the video, the reading. Okay, go back to the video. We need to have the speed, IA and IE. Okay, from here, you can read the speed already, right? It's 2228. And then from here, how you know which one is IA, which one is IE? Guys? Use your brain also, okay? Okay, since it's a YouTube video, also can drag it faster. What happens to the left-hand side and the right-hand side meter? This is measure the current, okay? You can see that the left-hand side keep increasing. How about the right-hand side? Is there any change on that meter there? Go back again, see. From the start is already 0.3 amp. Okay, on the left here is almost 0, 0.07, almost 0. Okay, because it's at 0 torque. So what makes the machine turn is the field winding or the excitation winding or the current at the excitation. So here we can know that on the right hand side here is the IE, and the left hand side, when we increase the torque, the current increases, so it's a IA. Then you can jot down the values here, okay? Speed, IA, IE no change. IE is a constant. Okay, it will just be a flat line if you plot it out. Well, IA will change according to the torque. Okay, and how about the speed? Of course, the speed will decrease if you increase, which you can see from here. This is an example for the plotting. Okay, we can see that the speed here, this is your speed but the speed here decrease, okay, according to the increase of torque. And then the IE should be a constant, okay, or a flat line. But I don't see where is IE. IE, I think is here. Okay, it's constant, flat. Okay, and the IA should increase. Okay, when you increase the torque. Okay, this should be the IA. And then this one should be your power input, power output. Okay, we can see that it's also quite linear going up. Okay, efficiency, I think is this. Okay, so that you can see actually it's saturated around here. Okay, after 1 here, actually is overload. We are overloading the motor. Okay, so, but this is for experiment. Usually, we try to run it below the nominal rating. This is 1 per unit here. This is if we keep running and running, the efficiency also won't increase already. Okay, the speed also almost, it may be cause the motor to stall or what. Okay, so usually this is over the rated value. This is the computer one. Okay, you can go and click and do it and watch it. The result I already paste it on the Google Classroom. You straight away can download and use it lah. The start speed, stop speed, you can observe what are the start speed, stop speed that I use. Or you can actually get from the graph also. Okay. This is to produce the graph, okay, in per unit. Make sure everything is plotted in one graph. Don't give me multiple graphs. That one is for shunt motor. Series motor is a bit tricky. It's not so direct because I don't start from zero. Why we cannot start the series motor at zero torque? If you look at this table here, these two value no need to do. Okay, this one impossible to do because the speed will actually is infinity. You also cannot get the result. Okay, the motor keeps speeding up. And then the procedure for series is you have to start it at a lower speed. Okay, we turn it to around 20% of its rated value. Means we run it at around 20% of 220 is how much? It's around 44 volt. Okay, start it at a lower voltage. So it is safe. For safety. Okay, after it runs, only I slowly increase the torque. Okay, and then slowly increase the voltage after there is torque. But you don't straight away put 1.43 at 44 volt, then it will stall also. So slowly increase the voltage and slowly increase the torque together. Okay. Then once it reach 220 volt with torque value maybe around 1, then you can operate it at 1.4 something or 3. This is to determine the nominal torque first. Okay. Let's look at the video. For the series motor, you see I start at 1.4. Okay. And a series motor only have one current flowing in, so there no need 2 meter. Either you can read 1.79 here or 1.76 is almost the same lah. Actually, no need the meter also can, but there will have some difference between the meter here and the meter or the display here also. So either you can tag here or tag here also can. So this 1.4 actually is the rated value. Okay. So in the video, I start in here in the middle. Okay, because if it is impossible to start from here, 0. So the next value I use is 1.54. Okay, 1.1 times 1.4, you get 1.54. Why I do like that? Guys, why I go up here, then only I go down like that? Because I'm already here, so it's easier I complete these 3 values first. Correct or not? Okay, then the motor is more stable. Okay, after I completed the higher torque value, then I continue to do the lower torque value until it's around this 0.2 per unit. And it's also more convenient and the motor more stable lah. Okay, you can see I start at 1.4. The next value you can see is 1.5, should be 1.54. Okay. The next value 1.68 and 1.82. That this should be the highest value already. Then I will go back to the next reading, which is 1.2 something. So make sure you fill up the table according to this sequence. Then I do lower and lower. This is actually the same procedure that if I ask students in the lab, I ask them to do like this, then it will be faster rather than starting at the lowest value, because once you go lower and lower, the speed will become faster and faster, the motor become more unstable. Okay, then the longer time you need to wait to get the result. If you hear the speed is keep increasing and increasing, okay, you actually need to wait for quite a long time for this to stop at a constant speed. But of course, I already cut short the videos. If not, you don't know how much memory it needs. Okay, so you can see that it needs some time to stabilize. Okay. Then I wait until it doesn't really increase too much already lah. Then I stop at there lah. Okay. The next thing I do, I think is at 0.14. I just want to let you see this motor keep increasing speed only. Okay, it's going faster and faster. So I increase the torque. Okay, then it will go slower. Then only I reduce the voltage a bit. Then I off the torque. Then only can off the machine. Okay, that is the procedure to off the machine also. Okay, slow down the voltage first. Okay, reduce the voltage. Then the machine will slow down. Then off the torque. After off, you can also listen to the machine. It's going up quite fast. Straight away go to around 4,000 RPM. This is only at around 100 volt. Okay, so that is for series motor. Okay, make sure you follow the sequence lah when you get the result. This is the computer one. You can also observe from the video. The compound machine. Oops, I didn't draw the equivalent circuit. You guys know how to draw the equivalent circuit for series motor? For example, this one no need to draw lah. This one is just a machine test system. This one go into here, A1, positive. Always start from the terminal. Start from the terminal. Positive go to A1. Oops, not using a coil for A1. Using a circle. This is A1. This is the motor, or you can put an M here. Then the A2 connect to D1. You can see here. Okay, A2 and D1 is together. This is just the terminal, the label. Okay, then got D1, of course, got D2 lah. D2 here go to the negative terminal. So it looks like this. So this is a series. IL equal to IA equal to ID also. So one current only. Next one is the compound. Okay, you can also see You can draw the equivalent circuit also, compound. Okay, again, start from the terminal. Positive, go into A1. I have a A1 here. Then the A2 connect to D1. It's same like a series motor. Okay. We have A2 or we have D1 at this point. And of course, this point here is this one, not using D2, using D3. Okay. So next we have the E and E1, E2. E1, E2 is connected in parallel. So I have my E1, E2 like that. So this is a compound. Again, the IL will be equal to IA plus IE. Okay. For this experiment, they make the connections as such so that the equation for KCL is the same as the shunt motor. From the book, it's not necessary you connect like this. You can connect the winding in the front also. Okay. You can also connect like that. This is also a compound motor. Okay. So here they're not using D1, D2, they're using D1, D3. Okay, to do this table here. Okay, it is this is for the 20% winding. Okay, how we know is they give a table here. Okay, if we connect the D1, D2, okay, it's use all of the winding. Just now you have a diagram like that. You have D1, D2, D3. If we connect D1 and D3 is using 20% of the winding. Okay, if we connect D2 and D3 is using 80% of the winding. If we connect like that, of course, use all the winding lah, 100% of the winding. So for this, the procedure is the same. The video, I think I should have start from 0 here, then go up, because this is compound lah. So it's more stable. But the top should be it should be operating at a higher torque compared to the shunt also, I think. Or it might have different nominal torque, so you guys have to verify here also. Okay, so 20% of the speed is also can get from here. Okay, this is the 20%. You have another 2 video here, which I do for the 100% and 80% winding. I change the connection. So this one you only observe the speed. Okay. If you use 20, 80 or 100% of the winding, this winding you can see is connected to the armature side. Okay, this side here. If change it to D1, D2 or D2, D3, what will happen to the motor's speed? Okay, plot all these 3 graphs together. Okay, this is only measure the speed. You only need to measure the speed. You don't need the current, no need other things. For the nominal speed, also make sure you use the same value as a base value. Okay, don't change. I think should be using the same nominal speed. Okay. Let's say we take the 20% as a nominal speed. Okay, then you can take that one as your base value. Same base value lah. If take different base value, maybe I scale it. You don't get the difference, but use your brain again, logical thinking. If you connect 100% of the winding to the armature there, how will the speed look like? Okay, which one faster, which one slower? These 3. How do I compare the speed of 20%, the speed of 80%, or the speed of 100% windings? Guys? Guys, which one will be faster? Which one will be slower? Of course, 80% is in between. That's why it's in the middle here. Huh? Guys, if we use all the winding at the D there, the D means the impedance is higher, or the resistance also is higher. Correct or not? So actually, this speed will be higher compared to this speed. Then lower speed is this. Correct or not? Your graph also must reflect this. Okay, if not, maybe you'll do something wrong in your calculation. What else? DC done, AC is almost the same. The procedure is the same, except that for the AC, we observe the starting current. Okay, so that you can no need to be very accurate. You can take the starting current, how much, then the I2 here is when it becomes stable. You can see that when I start the motor, the needle jump here. Okay, you cannot see, then rewind again. Start, then you see the needle jump to here. Okay. This is it's very far just now, so I'm doing it again. Same like doing in the lab. Okay, I ask the student do again and again. So this is the 1 amp. Okay, so you read on the top. So just now how much? Of course, you can pause the video lah. Where is the timer it jump? Not here, already stable. You can see where it jumps also is around 8.5. Okay, you don't have to be very accurate with it. This one just for observation. Okay, so it jumps until around 8.5, 0.85, 8.5. So you have to divide by 10 lah, because I'm using 1 amp for the rating. Then this is when it's stable. Okay. After it started, it goes down to 0.15. Okay. Around here. So you can see the range, how far it jumps. Okay. When it starts. So jot down the value, the rotation, you can observe it also. This one we can easily change the terminals around because it's for AC. DC we don't do that because we need to change all the position so that it follows the polarity. From here you can see there's a negative sign here indicating it's counterclockwise, and the light also is on the bottom. As you can see, it lights up at the bottom. If it lights up on the top, then it's clockwise. If it lights up on the bottom here, it's a counterclockwise direction. You can also see the direction when the motor slows down. This is for the delta observation. Just now it's also it will start a higher current, then will go down stable again. The rest of the procedure is same as a DC motor. Okay, same. You have to fill up the table here. You find the nominal torque value, then you find the actual torque value. Okay, and then for the star connection, the torque is 1/3. of the delta. Okay. This is for the power factor correction. Again, observe what will happen. Okay, they ask you to only jot down current and the power factor. The rest no need to jot down. Speed, voltage, all no need. Okay, it is just to observe the change of the current after you add in the capacitance. Again, make sure this nominal value you use is correct value. Okay, and then you can plot the graphs. Okay, not just this one. You have to plot the delta, and after you've done the power factor correction, okay, compare it side by side. Read the manual properly lah when you do the experiment or see what to plot. The rest, the appendix here, if you need some reference. If you don't know how to write discussion, you can write according to this, or these are the questions that if you don't know what to write for your discussion, you can ask this question yourself. Okay. Ask, or why happen like that? Okay. After you add in this, why is that? If you don't ask yourself those questions, then nothing to discuss also. Okay. Conclusion, what you observe lah. Okay, be more technical lah. Do not write the objective was achieved. Okay, write something more technical lah. Like for example, why the voltage need to operate at there? Why the torque is like that? Okay, when add in capacitor bank, what happened? How to improve what all those things lah. Advantage, disadvantage. Those are conclusion. Okay, which you summarize your finding again lah. Like the main point in your discussion, you summarize it and put it in your conclusion. Okay, do not say objective achieved. Okay, that is your 2-line conclusion. This is the participation mark, which you need to write. You need to answer some question I put on there also, so that your mark and your friend's mark will be a bit different. Okay, there's one question also I asked how to. There's an alternative way to connect this capacitor, but you can see this capacitor is connected like this. Okay, like if I label this as 1, this is at 2 here, then 1. This one here is connected to the second point, 1 here is connected to the second point, and so on. We can also connect the capacitor like that, and that can or not? This is also a circle, okay, which also gives us a delta. Correct or not? So it's not necessary you have to connect like this. I also can connect 1 to 1, but this 2 have to go to here 2, and then 1 here to 2. But then the line, this actually goes to line 1, line 2, and line 3. But you will have to label the line 1, 2, 3 way to connect it to also. So this one you draw it yourself lah. Okay. So use your brain, think. Okay. If we connect like this, then line 1, line 2, line 3, you have to rearrange it a bit lah, so that it doesn't short circuit. Because if looking like that, 1 to 1 here, if I also connect line 1 and line 2 here, is a short circuit. Correct or not? So I cannot do, if I want to change the connection, can also, okay? It's possible to do like that, but the line 1, 2, 3, you have to